Michio Kaku, one of the most renowned theoretical physicists of our time, has long been fascinated by black holes, those enigmatic regions of space where gravity is so intense that not even light can escape. Black holes have captured the imagination of scientists and the public alike for decades, primarily because they represent the ultimate mystery in astrophysics. For years, physicists have speculated about what happens beyond the event horizon, the boundary around a black hole from which nothing can return. While many theories have emerged, new developments in our understanding of quantum physics, general relativity, and cosmology have finally provided significant insights into this cosmic enigma. Michio Kaku, in his latest discussions, has shared that we are closer than ever to truly understanding what lies inside a black hole. To grasp the magnitude of this discovery, it's essential to understand what a black hole is. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycles, creating a singularity, a point of infinite density. Surrounding this singularity is the event horizon, beyond which all known laws of physics break down. For years, black holes have presented a paradox. While general relativity predicts that the singularity is a region of infinite curvature and density, quantum mechanics, the theory that governs the behavior of particles on the smallest scales, has trouble describing such extremes. The central challenge in understanding black holes has been reconciling these two seemingly incompatible theories: general relativity and quantum mechanics. While general relativity works incredibly well on the scale of stars, planets, and galaxies, quantum mechanics excels at describing the subatomic realm. Yet black holes require a theory that merges both, since they are massive objects confined to incredibly small regions, like a singularity. For decades, scientists have struggled to unite these two pillars of physics, but Michio Kaku believes we are on the verge of a breakthrough. One of the key revelations has come from string theory, the framework that Kaku has long been associated with. String theory suggests that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. According to this theory, these strings can describe both gravity and quantum phenomena, potentially solving the paradoxes that arise in black holes. This includes the infamous information paradox, which refers to the apparent destruction of information when it falls into a black hole, a concept that directly conflicts with the principles of quantum mechanics. Quantum theory insists that information can never be lost, yet black holes seem to obliterate anything that crosses the event horizon. Recently, there has been growing evidence that black holes may not completely destroy information after all. Instead, some physicists argue that information is encoded on the surface of the event horizon in a way that can eventually be recovered. This theory, known as the holographic principle, posits that everything inside a black hole can be described by information on its two-dimensional surface, similar to how a hologram encodes three-dimensional information on a two-dimensional surface. This idea has profound implications, suggesting that our universe itself may operate similarly to a hologram, where the reality we perceive is merely a projection from a deeper, underlying structure. Kaku has highlighted the importance of this principle in resolving the paradox of black holes. He explains that, thanks to the holographic theory, black holes might not be as destructive as once thought. Rather than obliterating everything, they could store and eventually release information in ways we don't yet fully understand. This suggests that the singularity might not be the end point of matter and information as previously thought. Instead, there may be mechanisms within quantum gravity that prevent the singularity from forming in the way we have traditionally imagined. One of the most exciting recent developments in black hole research comes from the Event Horizon Telescope, EHT, which in 2019 captured the first-ever image of a black hole. This achievement allowed scientists to directly observe the shadow of a supermassive black hole at the center of the galaxy M87. For the first time, we had a visual confirmation of the existence of event horizons, which had only been hypothesized based on indirect evidence. This breakthrough was a monumental step toward unraveling the mysteries of black holes, and Kaku has been vocal about the significance of this discovery. In addition to the holographic principle, quantum field theory has provided further clues about what happens inside a black hole. According to this theory, space is filled with tiny, fluctuating fields that interact with matter and energy. These fields become incredibly intense near the event horizon of a black hole, and Kaku suggests that understanding these quantum fields is crucial for deciphering the mysteries of the singularity. Another groundbreaking concept that Kaku has discussed is that black holes might act as bridges to other parts of the universe, or even to different universes altogether. This idea stems from the concept of a wormhole, a hypothetical tunnel through spacetime predicted by Einstein's equations of general relativity. While wormholes have not been observed, they remain a tantalizing possibility. If black holes are connected to wormholes, they could provide shortcuts through spacetime, allowing for the possibility of travel to distant regions of the universe or to parallel universes. Though this remains speculative, Kaku argues that understanding black holes could lead us to a deeper understanding of the true structure of the cosmos. One particularly exciting area of research that Kaku has discussed is the possibility of using black holes to understand the fundamental nature of time. Black holes warp spacetime so dramatically that time itself behaves differently near them. According to Einstein's theory of general relativity, time slows down near a black hole, an effect known as time dilation. As objects approach the event horizon, time appears to slow to a standstill, at least from the perspective of an outside observer. This raises profound questions about the nature of time and its relationship to gravity, which could have far-reaching implications for our understanding of the universe. In recent years, scientists have also begun to explore the potential of quantum computing to help solve the mysteries of black holes. Quantum computers, which leverage the strange properties of quantum mechanics to perform calculations far beyond the capability of classical computers, could be instrumental in modeling the complex interactions between quantum particles in the extreme conditions found inside black holes. Kaku has pointed out that advances in quantum computing could allow us to simulate black holes in ways that were previously impossible, offering new insights into their behavior and properties. Michio Kaku has long been known for his ability to bridge the gap between complex scientific concepts and the broader public. His enthusiasm for black holes is palpable, and his optimism about the future of black hole research is infectious. According to Kaku, we are entering a new era of discovery, where the mysteries of black holes are no longer beyond our reach. The convergence of cutting-edge research in quantum mechanics, general relativity, and string theory, combined with powerful new observational tools like the Event Horizon Telescope, has brought us closer than ever to understanding what lies inside a black hole. In the coming years, we may finally be able to answer some of the most profound questions about the universe. What happens to matter and information that falls into a black hole? Is the singularity truly a point of infinite density, or is there something beyond it? Could black holes be portals to other parts of the universe or even other dimensions? These are the questions that Michio Kaku and his colleagues are striving to answer, and the progress they've made is nothing short of remarkable. As Kaku often says, black holes represent the ultimate test of our understanding of the universe. They push the limits of our knowledge and challenge our most fundamental assumptions about space, time, and reality itself. But with each new discovery, we move closer to unraveling their mysteries. The journey is far from over, but one thing is clear. We are on the cusp of a new era in black hole science, and the answers we seek may soon be within our grasp.